Welcome to Maths with EJD. In this video, we'll be talking about machine learning in spectral analysis as a continuation of everything we've been talking about as far as it concerns spectral analysis. Okay, yeah, machine learning in spectral analysis is a very cool combination of two powerful tools. Machine learning, that's like something that has been gaining a lot of ground, in the past decade or so. And spectral analysis is a very classical stuff that is very useful in many aspects of our lives. So it's so sweet to see that machine learning has some expression in spectral analysis. So by way of introduction, spectral analysis, again, as we know, is a powerful tool for understanding the frequency characteristics of signals. Okay, so it's more like you want to take something from the time domain to the frequency domain. And when we talk about signals, it could be in forms of data sets or something, right? So by combining spectral analysis with machine learning, one can automate classification, anomaly detection, and prediction tasks in diverse domains, such as biomedical signal processing, structural health monitoring, telecommunications, and even geophysics, right? So the integration generally follows this pipeline. So to integrate machine learning in spectral analysis, we can generally have this pipeline. So we can have signal acquisition and preprocessing, spectral transformation, e.g. fast Fourier transform, Wells method, multi-taper methods. Then we can have feature extraction, often from the power spectral density. Then we can have feature selection or dimensionality reduction. I have a playlist on data science, right? So I have 60 videos where I've done different aspects of machine learning, like supervised learning, non-supervised learning, and even reinforcement learning. So we did something about dimensionality reduction using things like principal component analysis or TSNE and so on and UMAP too. Then we can talk about model training and classification, and then we have evaluation and deployment. Okay, so let's go straight and talk about feature extraction from power spectral density. So how do we extract features from power spectral density? So the power spectral density quantifies how signal power is distributed across frequencies, right? It is widely used because many physical systems and phenomena manifest distinctive signatures in frequency space. So talking about core PSD features, now like we've seen all along, we have the band power. This is integrating power spectral density over specific frequency ranges, e.g. delta, theta, alpha, beta in EEG. Then we have peak frequency, that's the dominant frequency where the PSD reaches a maximum. Then we have the spectral centroid, that's weighted average of frequencies reflecting the balance of spectral energy. We have bandwidth measures, which is the spread of energy around the peak frequency. Then we have spectral entropy, which is a measure of disorder and uniformity in PSD, useful for distinguishing structured versus noisy signals. Then we have ratios. So we have ratios of band powers, e.g. low frequency, high frequency power, or often used in physiology, right? So we have some advanced representations for feature all this. So we have logarithmic scaling. So taking log of power spectral density values to stabilize variance. Then we have parametric PSD fitting. So estimating autoregressive moving average or autoregressive moving average model coefficient as features. We've done things in this line in previous videos. Then we have multi-resolution features where we have things like wavelet-based PSD approximations. Then we have time frequency PSD features, extracting evolving PSD statistics from spectrograms or wavelet scalograms, right? So then we have dimensionality reduction, just like I told you not quite long. So we have things like principal component analysis, PCA, to compress power spectral density vectors into fewer uncorrelated components. Then we have TSNE stroke UMAP, useful for visualization and clustering in reduced dimensions. Then we have feature selection methods like ANOVA, mutual information, lasso, that's some regression thing to retain only the most discriminative PSD features. So it's more like you have power spectral density and you want to get the most important features from it. So the machine learning can play a very powerful role there. And don't forget, by the way, if you are really interested in machine learning, I have 60 videos on data science, which machine learning is a subset of data science, by the way. So where I've treated all of these things. So just check out data analysis with EJD on my channel. Check out the whole playlist. Then we have classification based on frequency content, right? So another way machine learning can come into power spectral density, spectral analysis is for the classification based on frequency content. So once PSD-based features are extracted, machine learning algorithms can learn to distinguish between classes based on frequency characteristics. So we can have classical machine learning approaches like support vector machines. I mean, I treated all of these I think all, yeah. I think I treated all of these algorithms in the playlist on data analysis, data science. The data analysis is different from data science. It is in data science that you get machine learning. So under data analysis, that's where you'll be talking about NumPy, pandas, and visualization tools like Matplotlib and Seaborn, right? So classical machine learning approaches, you can use support vector machines, which is effective when frequency bands show sharp discriminative patterns. So this helps you to delineate between frequency patterns in spectral analysis. Then you have random forest, which is robust to noise and useful when combining PSD with additional metadata. Then we can have k-nearest neighbors, KNN, which is simple distance-based classification using PSD feature vectors. Then you have linear or quadratic discriminant analysis, LDA/QDA, efficient for low-dimensional PSD features. Then we have deep learning approaches, like convolutional neural networks, CNNs, which is applied directly to power spectral density matrices or spectrograms as images. Then you have recurrent neural networks, RNNs slash LSTMs slash GREs. By the way, of course, you see these things are things that are related to time series analysis. So spectral analysis is basically dealing with time series analysis. So the only thing is that you're taking the time series that you have from the time domain into a frequency domain. All right. So recurrent neural networks capture sequential patterns when PSD evolves over time, right? Then you have autoencoders. I treated all of these also in the data science playlist. So learn compressed latent features from power spectral density, which can be used for clustering or anomaly detection. Then we have some application examples, like in biomedical signals, EEG, ECG, EMG, all these electrocardiogram or something like that, So like when an X-ray is done and some things are checked in the body. So PSD-based classification for detecting epilepsy, sleep stages, or arrhythmias, right? Then you have structural health monitoring. So identifying cracks or fatigue in mechanical systems from vibration spectra. So of course, in moving parts like in an aircraft or machinery in a factory, so we can use this. Then we have speech or audio recognition, distinguishing phonemes, emotions, or environmental sounds. Of course, as we speak, we make sounds like like in a language like Kosa, where they have like that kind of clicking thing. So this can become useful there or in every other language too. Like, where you get to talk about fricatives and all of these kind of things, labial sounds, fricative sounds, and everything. Then you talk about telecommunications, where you can classify modulation schemes or interference patterns from spectral signatures. Then after all of that, we talk about after you've done all the necessary things, you can then go ahead and talk about evaluation and deployment. We talked about deployment a lot. Evaluation is, using some metrics to measure the accuracy of your machine learning algorithm, right? So, so when applying machine learning to power spectral density-based features, evaluation and deployment strategies are crucial to ensure reliable and interpretable results. So we have some metrics. Of course, I mean, we talked about this whole metric thing also in the data science playlist. So we have accuracy, which is proportion of correctly classified samples. So I think this is where you get to talk about false positive, false negative, true positive, true negative, and all of these things. So you have F1 score, which is harmonic mean of precision and recall, useful for imbalanced data set. They're all based on the whole idea of false positive, false negative, true positive, and true negative. So there's a way all of this come together to define each of these metrics. And you have ROC-AUC. So this is area under the receiver operating characteristics curve, effective for binary and multi-class problems, right? Then you have the confusion matrix, which provides detailed interpretation of class-specific performance. Then you have cross-validation, all right? So purpose of cross-validation is to prevent overfitting by evaluating models on multiple folds of the data. I mean, you can get clear understanding of this by watching the playlist on data science, EJD. Then recommendation, you can use stratified k-fold cross-validation, especially with small PSD data sets. Then you have real-time constraints. So efficient feature computation is vital in embedded or online systems. Instead of full PSD vectors, compute band powers or a set key of key descriptors. Then consider trade-offs between accuracy and latency in deployment scenarios. Then talking about interpretability, so we have feature importance analysis, which reveals which frequency bands drive classification. So of course, there are many variables driving the system, but there are some that are dominant that, if you want to select the most important features, if you eliminate the others, they don't really amount to so much, right? And that is why we do feature importance in machine learning and slash data science, if you like. Then talking about interpretability, all right. Feature importance reveals which frequency bands drive classification, just like I said. And you have tools like the sharp values, that's sharply additive explanation. I think we did all of this in the playlist for data science. Then you have permutation feature importance. Then for the benefits of this, it helps to validate models and connect results back to physical or physiological meaning. Then for this whole machine learning story I've been telling, we have a very lengthy Python implementation. Well, maybe I'll just run through quickly. Of course, if you're interested in this code, you can just reach out to me somehow. For the other programming things I've done, like Python basics, data analysis, data science, Excel, you can look at the description box to find a link to the Google Drive where you can download them. But for this one, I've not been uploading them. Maybe I should create it. Well, I think it's too late. Maybe, I guess it's too late now also. Or I don't know if there's need for it, I can do that later. But if you I definitely need this, I can send it to you. So for Python implementation now, so we're talking about machine learning with power spectral density features. We have PSD via Welch, feature extraction from PSD, classification by frequency content. So, we import. So here now we have a combination of machine learning and spectral analysis. You know the usual things we've been using for spectral analysis. We've been using NumPy seems to be everywhere. NumPy is useful for data analysis, so it's used for it's good for data science, and we'll be using it a lot also for spectral analysis. So now it's here again. SciPy.signal is unique to spectral analysis, like we've been saying. Then SciPy.stat, we have gmin spectral analysis. Then when you see all this scikit-learn, sklearn, these are scikit-learn for basically machine learning and the necessary train test splits, stratified k-fold, and all of these things. Then the pipeline, standard scalar, and so on and so forth, support vector machine, random forest classifier, and all that, right? Then we have the PSD computation. Now, so we defined several functions. So we have compute PSD Welch. We've been doing this a lot, so you can pay attention to the coding like that. We've done that a number of times. Then for PSD feature helpers, we now have underscore band underscore mask, and need to take frequencies, F min, F max, and all of this. Then you have the band power, the spectral centroid with all the necessary definitions for their possibility. Then you have spectral bandwidth, peak frequency. So we need all of these things. Then we have spectral entropy too that we talked about in the theory. Then you have spectral flatness, band power ratio, right? And then again, we have feature extraction from PSD. So you now want to know what is really important in this whole thing. So you have frequencies, NP, NDRA, PSD, NDRA, bands none. Then extract a rich feature vector from frequency and PSD. So you have band list of name F min and F max. So you have generic bands for broad signals, adjust for your domain. So you have bands. So you have ultra low, low, mid, upper mid, and high. So and then you have the feature. So you now you have this. You open this this is this set we should call this now, and then you pick the ones that are best later. Then for the total power we have the calculation here. For the per band powers we have them here. Then we have a few useful ratios like BP low, BP high, and all of these things. Then we have ratio low high, all of this here. And then we have peak and shape descriptors. So you have fit peak underscore frec, like all this bandwidth centroid and the rest of them. Then you have synthetic. Now we are using synthetic data since we don't have a proper data, but I mean, if you're working with proper data, you can bring in your own data here. So this all other thing we are doing is to generate synthetic data for what we need to do. So we build the time series as a sum of sinusoids plus white noise. We've done that a lot, by the way, under spectral analysis. Then here we're making synthetic data sets, number samples per class, integer 300, fs float 200, duration. So with this now we can generate synthetic data. So we have two classes with distinct frequency content. We have class 0, energy dominated by 6 hertz and 12 hertz. Class 2, dominated by 18 and 36 hertz, like that. So you can see it's quite a lengthy code. I could have broken it up, But I mean, I think it's also fine that we have it together. So for easier implementation, all right. So train and evaluate classifiers. So this is where machine learning sets in now. So once you train and evaluate classifiers right here, we've done a lot of this under the data science thing. Then you can then run the demo. Okay, so I'll just do Control Enter here. Of course, you can expect that it's going to take a lot of time because we have a lot happening in one cell, right? So you can see it's running. Okay. Once it's done running, then we can go look for the results. Okay, so this is machine learning, the beautiful marriage between machine learning and spectral analysis, like that. Okay, now it's done. So let's go and see what we have. No errors, thankfully. So let's see what we have. Okay, first of all, we have feature count. We have 17 features in all. So top feature for of the 17, we have the top features to be bandwidth, BP high, BP low, BP mid, BP rel high, BP rel low, BP rel mid, BP rel ultra, and so rel, and then BP rel ultra low. Then we have support vector machine. We have RBF five-fold accuracy. That's 1 ± 0 0. Then RF, we have five-fold accuracy. This. Then for the SVM test precision. So we can see we have most of the values are perfect, like 1.00. So of course, maybe that's far from reality, but I mean, based on the synthetic data we have, so the values look pretty good. All right. Then we have the confusion matrix here for the support vector machine. Then for the random forest classifiers, the values are looking pretty good. So precision of 100%, 1.00 means perfect, right? But of course, we use synthetic data. So when you get real data, you may not expect to get exactly the same thing. Then we can visualize the synthetic signals, right? So this is the code to do that. So we add a new code cell to plot examples of the synthetic signals for each class to show their time domain characteristics. So, we have this coding to do all of that job like that. You can settle down to understand. So here now we have example synthetic signals by class. We have the one of class 0 dominated by 6 and 12 hertz like we saw the other time. So we have the peak amplitude somewhere between 2 and 3 value like that. Then we have the amplitude. Okay, the example synthetic signal class 1. We also have this kind of stuff. Then we can also visualize power spectral densities of synthetic signals. So here we compute and plot this power spectral density for the example synthetic signals from each class to visualize their frequency characteristics. So I run this now, and then of course we see things we have been used to seeing previously. This is class 0 and this is class 1, right? The peak for this is somewhere above 0.4, and for this one it shoots over 0.3. Now we can visualize feature distributions. This talks more of machine learning. So the reason here is to generate the synthetic data set and then visualize the distribution of a few key power spectral density features for each class using box plots, right? So box plots are very good for seeing outliers, for seeing the spread of a data set and things like that. So we have all these box plots telling us the stories of the spectral density here. So distribution of key PSD features by class. So we have distribution of BP rel low, rel high, ratio low high, peak frequency, distribution of centroid, distribution of entropy, and so on and so forth. Interestingly, we have some explanation of those things you have up there. So data analysis key findings now. So we see that example synthetic signals for class 0 exhibited different time domain characteristics compared to class 1, consistent with their generation parameters, different tone frequencies. Then the power spectral density plot revealed distinct frequency domain characteristics for the two classes, with class 0 showing dominant power at lower frequencies around 6 Hz and 12 Hz, and class 1 showing dominant power at high frequencies around 18 Hz and 36 Hz. Of course, you can actually refer to the diagrams to see what this is all about. Okay. So, so at lower frequencies, you see class 0 having dominant frequencies, but this one is happening at higher frequencies than class 0. That's part of what the explanation tells us. So box plots of key PSD features demonstrated clear separation between the two classes of features, such as BP rel low, BP rel high, ratio low high, and peak frequency, indicating their effectiveness in discriminating between the classes. So if you use all this now, you can actually distinguish between the classes. So you have class 0, class 1. So you see class. So for distribution of BP rel low, so class 0 is up there while class 1 is down. So class 1 is okay for real BP underscore rel underscore high, and then class 0 is up for that low one. Then distribution of peak frequency, class 1 is up there. Distribution of centroid, class 1 is up. Then distribution of entropy, class 0 is up, like that. So we see all of those. So it means they're very good. So those shows that they're effective in discriminating between the classes. Then talking about insights or next steps, how do you know they're not very good? So if in most of the places you have class 0 and class 1 behaving about the same way, so it won't be a good way to distinguish. So here you have all the peak frequency, centroid, and all these things right there. So insights or next steps. The chosen power spectral density features appear to be highly discriminative for the synthetic data set, suggesting they are suitable for training a classification model, right? The distinct frequency content between the classes confirms the frequency domain analysis is a valuable approach for this type of signal classification problem. In summary, we see that machine learning enhances spectral analysis by automating the detection of subtle frequency domain patterns. Then feature extraction from power spectrum density provides meaningful representations of signal energy distribution, while classification models leverage these features to differentiate between conditions, states, or events. Together, they form a systematic pipeline applicable across engineering, health, and science domains. In the next video, we'll be talking about some case studies of spectral analysis. So the real applications in in biomedicine, in finance, in I think in geology or something like that. I'm not too sure. So watch out for that video. It's going to be really interesting. All right. So with this, I come to the very end of this particular video. Let me know how helpful this is for you. And if there's something you'd like me to try out, feel free to let me know also. If you have subscribed already, I must say thank you so much. And I know you're having a nice time on this channel already. If you have not subscribed, of course, you don't want to keep missing this very useful learning, right? So go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. All right. Ultimately, I mean, beyond that, you can also click on join to become a member of the channel. And that comes with some special privileges like having a one-on-one conversation with me based on our agreements and all that, right? So don't forget to like, comment, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right, keep doing data right, keep doing Python right. Bye.